So we're going to take a look at some different types of energy that you'll see in your physics classes and learn a bit about how to use them. So one thing to think about is something moving in the situation you're looking at? Well, then it has kinetic energy that you'd find with 1/2 times mass times velocity squared. Is something way up high? Well, then that object has gravitational potential energy. That's given by mass times the acceleration due to gravity times its height. And finally, is there a spring in the problem, and is it stretched or compressed? And in that case, you'll have some potential energy stored in the spring, and that's going to be given by 1/2 times the spring constant k times the stretch or the compression distance delta x, and then you square that distance. And another thing that you're going to have to think about is friction wasting energy in the problem? Is something scraping against a surface? And in that case, the wasted energy is just going to be found by taking the friction force times the skid distance. So let's take a look at a scenario that would use some of these ideas. And so what's going to happen here is we're going to have a block that starts off moving at the top of a ramp. And the block is going to slide down this rough ramp and then come in contact with the spring that it's going to squish a certain distance. Delta X, we'll call it. And so the idea is to figure out how far will that spring get squashed when the block slides down this rough ramp. Well, so the general framework that you want to use is conservation of energy. So a way I like to set it up is to say, well, the energy present in the system before equals the energy that's present in the system after, plus any that might have gotten wasted along the way. And so what we're really going to do is keep track of, well, the energy that you have in a before state of the system, which I'm going to take as the top of the hill here, with the block moving at the top of the hill. Afterwards, you could choose a place, say down here where the surface is flat, where the block is moving, but then the problem is that's not going to teach you much about the spring just yet. So what you might as well do is just treat the after state of the system as the moment when the spring is at its maximum compression, and then you can just go straight for sort of solving the problem. And so we're going to use this framework. Well, before, when the block is up high, it has gravitational potential energy, mgh. But don't forget that it's also moving. So it has a velocity 1 meter per second, so we're going to use 1/2 mv squared to represent its kinetic energy. This is all the energy it has before. And so what we need to do is keep track of where these joules are going to go. Well, one place they go to squashing that spring. And so the after state of the system, you have energy 1/2 kx squared, which is the potential energy of a squash spring. Right? The block's no longer way up high, so it doesn't have any mgh, and it is not moving, and so there's no v for there to be a 1/2 mv squared. But along the way, as it scraped its way along this ramp, we're going to waste energy in the form of friction force times distance. Friction force, when you're on a ramp like this, is going to be coefficient of friction times normal force, which in this case, when you're on a ramp, is mg times the cosine of the angle of the ramp. And then we're going to multiply that force, mu mg cos theta, we're going to multiply that force by a distance d. And so this is all set up. The issue here now that makes things a little cumbersome is you have this value, this height h, but we can get h in terms of the ramp length d and this angle 40. D would be like the hypotenuse of a right triangle, and this side here where I'm wiggling my mouse, that is the height, and that's going to be d sine 40. I picked 40 because that leg would be the leg of the triangle opposite the known angle, and so you're going to want to use sine for that. And so this is our basic setup. The physics is really done at this point. Now we just need to substitute in values. So we'd have m being 2 times g being 10 or 9.8, depending on what your teacher wants you to use. And h is going to be, well, 3 times the sine of this 40-degree angle, since our ramp is 3 meters long. Plus, well, 1/2 mass being 2 times the velocity of 1 squared equals 1/2 times the spring constant k times the squash distance squared, and that's what we're solving for, plus mu times the mass times g times cosine of the 40-degree angle times the distance d. And when you solve this, you learn that that spring gets squashed, well, 32.5 centimeters or 0.325 meters. So the upshot here is you want to use this framework, say that the energy that's present in the system before is going to be equal to whatever energy is present after, plus any that might have gotten wasted along the way. And the way to figure out what was wasted along the way, friction force times the distance. Well, hope you find that helpful, and hopefully it gives you a good little review about different types of energy you might encounter.